Hello guys, today we are going to look at the heading of applications of redox reactions, and under this heading we will look at the topic of combustibility. Well, at one point or another we have always wondered whether a given substance is combustible or not, and after this session you will be able to precisely determine that. Let us say we are given a sequence of compounds starting with diborane, that is P2H6, methane, CH4, ammonia, NH3, water, H2O, hydrogen fluoride, HF, and let's say we are asked to determine whether these substances are combustible in an atmosphere of oxygen or not. Well, the first important thing to realize is that combustion actually represents a vigorous redox reaction, and therefore the oxidation numbers and electronegativities, these are going to play a critical role in this determination. So the first task in our hand will be to write the oxidation number of each and every element present in this sequence of compounds. So let's do that together. So we see that in diborane, boron is present in +3 oxidation number. Each hydrogen is present in -1 oxidation number. In methane, the corresponding oxidation numbers are -4 +1. In ammonia, -3 +1. In water, +1 -2. In HF, +1 and -1 respectively. After this, we are going to strike out those elements which are present in already their highest possible oxidation numbers. And here we observe in the first case, boron is present in its highest possible oxidation number, that is +3, so we strike it out. In methane, it is hydrogen, so +1 is its highest possible oxidation number, and therefore we strike it out. Similarly, in ammonia, we strike out hydrogen, water also, hydrogen is struck out, and finally in HF also, hydrogen is struck out. The point being that the element which is present in its highest possible oxidation number cannot be further oxidized, and therefore these elements are not of any interest to us. Now, coming to the leftover elements, we will write their electronegativities and compare their electronegativities with that of oxygen. So let's do that together. So hydrogen in the first case, we'll write the electronegativity 2.1, carbon 2.5, nitrogen 3, oxygen 3.5, fluorine 4, and oxygen here of course once again 3.5. Now, the next question we should ask ourselves is this element more electronegative than the element over here or not? And we observe that oxygen is indeed more electronegative than hydrogen, and therefore definitely capable of oxidizing hydrogen, and hence B2H6 or diborane, it is going to be combustible. Coming to methane, we will compare the electronegativity of oxygen with carbon, and once again we discover that oxygen is more electronegative than carbon, and hence methane is also going to be combustible. Coming to ammonia, again we see the same thing. Oxygen is more electronegative than nitrogen and hence capable of oxidizing it, and hence this particular compound, that is ammonia, it's also going to be combustible. Comparing oxygen with the oxygen in water, we see that they are of equal electronegativity, and therefore oxygen cannot oxidize oxygen here, and hence water is not going to be combustible. So we'll strike out water. And finally, we observe that oxygen is actually less electronegative than fluorine, and hence there is absolutely no question of oxygen oxidizing fluorine, and hence HF is also going to be non-combustible substance. So therefore, we conclude that out of this sequence of 5 compounds, the first 3 are going to be combustible and the last 2 are going to be non-combustible. But that's not all. We can actually also see that the difference in electronegativity goes on decreasing when we move from the first case to the third case, and therefore it can also be concluded that diborane is going to be the most combustible compound among the first 3, and the combustibility will decrease from diborane to methane and finally to ammonia. So with this, we will end this session, and in the next session, we'll see how to determine the stability of a given sequence of compounds. So that will be all. Take care.